Hey everybody, so like I had mentioned last video, we left off talking about acids and bases. The last thing that we really did was we were talking about strong acids, strong bases, weak bases, and what does that actually mean when we have a solution. And so when we have our solution, we have our strong acids. Those are things that ionize completely, meaning there's no equilibrium, like none whatsoever. So instead of drawing that equilibrium arrow that you usually use up to this point, we're not going to use that for a strong substance because it totally turns into products. On the other hand, weak substances like weak acids, weak bases do have equilibrium. So when we have equilibrium, we end up having significant amounts of both reactants and products. And so what I'm going to hopefully show you in this video is how do we do calculations for the strong acids, strong bases. All right, so when we're dealing with a strong acid or a strong base, sorry, I know this is not super clear. I don't know how to make it clear. There we go. Okay, it's probably gonna like focus in and out constantly. That's what's gonna happen here. When we're dealing with a strong acid or a strong base, like I said, ultimately what we mean when we say a strong substance is we're talking about a substance that has no equilibrium. Now that's not totally true, but if you think about it that way, it's true enough for what we're doing. So just to give you that example, let's say we're talking about a strong acid. And we'll use HCl just because it's a really common strong acid, something we learned about previously as one of the strong acids. Okay. So when we have an acid, remember we place it in water, and when we place it in water, it's going to actually react with the water. So we have our molecule of HCl, we have our molecule of water. HCl is the acid, so it is going to take that proton and it is going to donate it. That's the whole point of a substance being an acid. And so as it donates it, this is a one-way arrow. Because there's ultimately not really equilibrium, there is no equilibrium arrow. We only really have products produced in this reaction. So that proton moves over and we get H3O plus, what is called our hydronium ion. And that hydronium ion is also with the conjugate base of hydrochloric acid, and that's Cl minus. So what we end up getting is that H moved over, and now you have H3O with a positive charge. You end up just having Cl all by itself with its negative charge. And so that's what we end up when we have a strong acid, is when the reaction takes place, pretty much all that's left is this stuff. You can think of it as being like a million of these for every one of those, right? And at that point, you might as well not even talk about this stuff. So that's why we consider this to be a one-way reaction. So when we're dealing with that one-way reaction, what we need to think about is how to calculate. So we're going to look at calculations with a strong acid. Whenever we have a strong acid, because there is, there we go, okay, wrong way, there we go, okay, because there is no equilibrium, then all we have to do is use stoichiometry. That's really the key when it comes to working with strong acids. Because they are strong, use stoich. Strong, use stoich. So we have HCl. That's going to be my example here. Maybe I'll write the actual question over on the side for us so that you can see. In example number 1, we're going to say, what is the concentration of H3O plus if the concentration of HCl is 0.050 molarity. And I know I wrote that in a really tiny squish space, but just that's the way it goes. Deal with it. Okay. So the first thing I'm going to do is write my balanced equation. We're dealing with stoichiometry. Remember your 4 steps of stoichiometry. Balanced equation is my first one. This equation is an ionization reaction. So the acid reacts with water, produces hydronium, produces the conjugate base. We know that the concentration of hydrochloric acid is 0.05 molarity. So what we need to do next is use stoichiometry. So we would go to moles, but this is a molarity, so that's good enough. And now we're going to use our molar ratio. So we're going to take our molar ratio of 0.050 molarity for HCl. We're going to multiply by the molar ratio. And so for every 1 mole of H3O plus, there is 1 mole of HCl. That gets rid of my HCl's. And the concentration of H3O plus is 0.50. Let's keep in mind our sig figs here. 0.050 molarity. What you probably noticed here as we tried to find that concentration of H3O plus is that the concentration of H3O plus is the same as HCl. And it'll actually work out with strong acids that you always end up getting the same concentration for H3O plus as you did for your original acid. And that's because it's always going to be a 1-to-1 ratio. Every single time that we do this, you're going to get a 1-to-1 ratio. And because of that 1-to-1 ratio, your concentration of hydronium is always going to be the same as the concentration of acid. So ultimately, working with a strong acid is relatively easy. You don't actually really need to do a ton. You just have to use stoichiometry. And because it's a 1-to-1 ratio, it's easy stoichiometry. So let's take a look at how this changes when we're dealing with a base. So we're going to look at calculations when we're dealing with a strong base. Now, the calculation itself is going to look really similar. We're going to use stoich. And the reason that we're going to use stoich is because it's still that total movement towards products with no reactants left over. The only real difference here that we're going to see is that we're dealing with ionic substances. So HCl is actually a covalent substance, and it ionizes by reacting with water. The strong bases are all ionic substances. Now, I'm going to write my equation with it being aqueous at the start. I'll explain why in a second. And it's going to dissolve into its component ions. Now this time I need to be a little bit careful because I have a 2 with the hydroxide. I need a balancing coefficient of 2. Okay, for those of you who are wondering why I put aqueous, I put aqueous because I'm really not dealing with the stuff that's a solid in the solution. So again, think about like making iced tea. If you wanted to know how many like iced tea ions there were, it doesn't matter how much solid there is. What matters is how much of that stuff got dissolved, how much of it is aqueous. So if we want to know, in this example, let's say we want to know the concentration of OH minus, we need to know how much BaOH2 was dissolved. Okay? So we're going to do this example, and in this example, this is example number 2, what we are trying to find is what is the hydroxide concentration if the concentration of barium hydroxide is 0.010 molarity. So we know this concentration is 0.010 molarity. Our question is how much hydroxide is there going to be? So again, this is a strong substance. Strong substances use stoich. So we're going to have 0.010 molarity barium hydroxide. We're going to use our molar ratio, but this time we want to find the concentration of OH minus from the concentration of barium hydroxide. And it is a 2-to-1 ratio. So the concentration is 0.020 molarity. And that is the concentration of OH minus. It's a little box around it. There we go. Okay. So remember, when you're dealing with a strong substance, whether that strong substance is an acid or whether that strong substance is a base, you are doing the same thing. You're using stoichiometry. And we use stoichiometry because it's a one-way arrow. So that is ultimately the lesson here. If you're dealing with a strong substance, use stoichiometry to find your concentrations. What we're going to be asking you is questions where you have to find H3O plus when it comes to an acid and OH minus when it comes to a base. What I would recommend is at this point in your workbook, you should have some questions for, I believe, 3.3. It might be 3.2. I don't know. I don't remember the numbers anymore. But whatever the number is, you should do that practice for the strong acids and strong bases. Okay, thanks, and see you next time.